The following example, we will implement something like a matched filter but using convolutional neural networks. So it just serves as a short introduction into neural networks and its terminology. We are going to use PyTorch, so we will not go in detail here how PyTorch really works, but it's more an example to get a short introduction. So observe that we got a high peak for detection of our signal, but the peak was somewhat broad, which makes determining the precise location of the signal more difficult. So this is because we specified as a target for our optimization that we want to have a high peak, but not necessarily a narrow peak. To remedy this, we can use numerical optimization instead of our closed form solution for matched filters. So what we will do, we will implement our filter using a one-dimensional convolutional layer, so it's the conv1D PyTorch without a bias and without the nonlinear activation function. We also need for this example training signal. So here our signal to detect, so rank function, and a target signal, which is the desired output of the convolutional layer, which the optimization should reach as closely as possible during the optimization or training. So here our training set will be our ramp, and our target will be just signal with zeros and a peak 1 at position 16, which is the same position maximum of our ramp. So observe that for the target Y, we specified a single peak at the position the filter should detect the signal and zeros everywhere else. And this also leads to a minimization of the output outside the signal detection. And we didn't have this in our closed form solution. So we will specify our convolutional detector layer using conv1D, input channels, output channels, the kernel size, stride, padding, resetting bias to false. Observe that the padding equal to kernel size minus 1 leads to a causal filter, meaning that all its inputs are not in the filter. So this implements our linear filter as detector. And the optimization we apply will minimize the mean squared error. It's also called L2 loss function. So we can let the optimization run on the same ramp function as before and display the output of the detector when we use as an input the clean signal and a noisy signal. So here is our example, PyTorch. So here is just an auxiliary function that we are changing dimensions of our input signal, our signals to the dimensions that PyTorch is expecting. So here, for example, have a signal vector like a mono audio, and then we need to add some dimensions, a dimension for our channel, the one channel, and the dimension for the batch. Here, just one batch. And here is how we create the PyTorch model. Here we put the layers, so we are using a convolutional layer. Here the parameters. We must also define here the forward function. Then here what we are doing is we having an input signal ramp, and we convert to the dimensions that are expected by PyTorch. Our target we also convert. We can see the shapes of our input signal, our target. Then we generate our model here, so defined as a class here, convnet, our model now, convnet. We need also to define the loss function, mean square error. Also need to choose which kind of optimizer, so we have stochastic gradient descent, we have many different optimizers that are suitable for different things. And we also have to define how the experiment will go. So we have many epochs. Then we have here loss function. We need to also have these steps backward and the optimize step. Here we can save our model, and then here we are having, for example, when we have a noisy signal, so it's a ramp plus noise, and then restrained and prediction, give it an input to the model to see what goes the output. So here is how training goes. This step here is just that we don't want to print the loss every single epoch, but every 100 epochs. So epoch number, loss function, and then we have here, for example, when we have we'll have our ramp, the signal. Here is the noisy signal. So this is the weights PyTorch calculates after training. We see we obtain these coefficients. So this is a time reversed impulse response, and we see it's a different impulse response than the matched filter, also because this optimization is trying to minimize the output outside the detection point. We didn't have this in our matched filter. Matched filter was simply the time reverse ramp signal. So now when we input clean, input would be here, clean input, the peaks here in blue. We have the output of our filter, this peak here. If we use a noisy signal, so this, the output of our filter in here in orange. So the result of the detection, clean and noisy signals. Observe the peak at the detection point is indeed much more narrow than when we used the matched filter.